Okay, in the previous video we went over the establishment of limits from tolerances, plus or minus this, whatever it is. We can establish two numbers, an upper limit and a lower limit. Based on the gender of the part, then one of those limits becomes the maximum material condition. The other limit becomes the least material condition. And we'll use those sizes, or those limits, in GD&T, or we can use those limits in GD&T to adjust the size of the tolerance zone that is stated in the feature control frame. So what I've done here now is I'm going to go back to tolerances of form, just because we're a little more familiar with it. And we're going to use the material condition modifier to adjust the tolerance zone for the straightness of the center line of a shaft. You remember from form we had control of surface elements and derived median elements. The derived median element of the shaft is its center line, and we know that we're controlling the center line because the feature control frame is attached to the size dimension of 1 inch plus or minus 5. Okay, so now I don't know what kind of resolution this camera has or whether you can see this real well. So I have blown up the dimension and the feature control frame from here to here so that you can see exactly what's going on. I've taken the 1 inch plus or minus 5 diametral tolerance and turned it into limits of 1 inch plus 1 inch 5 thousandths and 995 thousandths. It's a shaft, so it's a male feature. This is the maximum material condition. This is the least material condition. And we've done everything that we did in that previous video. So now we're ready to start looking at material condition modifiers, where they show up in the feature control frame and what they do to the tolerance zone. Okay, so let's look at this feature control frame. We know that we're controlling the straightness. We know that there is a diametral tolerance zone of 10 thousandths that is controlling that straightness. So we have a tolerance zone about the center line of that shaft. It is a diametral tolerance zone, and that diameter is 10 thousandths. All right there, all buried in that, and this is what you have to either visualize or draw from this feature control frame. That is the reading of the feature control frame. All right, so now let's look at material condition and see how it comes into play. Okay, so we'll look in the feature control frame, and all the information in the tolerance zone is defined here. So if we're going to do anything to the tolerance zone, it will show up in here. So right now we see nothing in that feature control frame except the size of the tolerance zone. In the old days, you would have seen an S in that location. That means regardless of feature size, and for you that means that the tolerance zone is a diameter 10 thousandths. It will always be 10 thousandths. Nothing you can do can change it. So if we look at a table of the various sizes that we could have, from 1 inch 5 thousandths at maximum material condition to 995 thousandths at least material condition, and stepping down thousandth by thousandth, let's take a look and see what the size of the tolerance zone diameter would be for each one of these sizes. Okay, in the case where it is a regardless of feature size, no symbol, but that's what it means. If there's nothing here, it is regardless of feature size. We can very easily do that. We know that when the shaft is at maximum material condition, the tolerance zone is 10 thousandths. When the shaft is at 1 inch 4 thousandths, it is 10 thousandths. 1 inch 3 thousandths, the tolerance zone is 10 thousandths, and all the way down to the least material condition of 995 thousandths. that tolerance zone starts at 10 thousandths, it ends at 10 thousandths, and it will always be 10 thousandths because there is no material condition modifier there. You have to sort of imagine that there's an S there, but if there's nothing there, the tolerance zone does not change. Whatever is stated in the feature control frame, that's the size of the tolerance zone, and that's what it will always be. Those are easy. Those are the easy ones. But they don't take advantage of the power of GD&T to allow you to adjust the tolerance zone. Now again, I think in a previous video I mentioned that this is sometimes called bonus tolerance, in that if you have control of this shaft, if you can control it very tightly, you can pick somewhere in here that you're going to make all those shafts. Let's say that you don't want it to be at maximum material condition because all you'll get is 10 thousandths. If you can control the process well enough and make them at 996 thousandths, you'll be able to adjust that tolerance zone upward, and the shafts can be that much less straight and still be acceptable. Let's see how that works. Okay, so I'm going to put a material condition modifier in the feature control frame, and now we're going to evaluate step by step to see what the size of that tolerance zone is. It's remarkably simple, but again, you almost have to do it on paper or on a spreadsheet so that you make sure that you know what your tolerance zone is for a given size. Okay, now the way to read this when you see that material condition modifier is, I have a straightness tolerance zone of 10 thousandths diameter when the feature, when the shaft is at maximum material condition. Okay, that's easy. When that shaft is at maximum material condition, the diameter of the tolerance zone will be 10 thousandths. That will be, in this case, or any case where we have a material condition modifier, that will be the smallest tolerance zone that you'll ever have. You'll always have at least 10 thousandths, but that will only apply when the shaft is at its largest or at its maximum material condition. Let's say the first shaft you hit right at maximum material condition. It measures 1 inch 5 thousandths. You have to check the straightness. You get a 10 thousandths diameter straightness tolerance zone. The next shaft that you make is a thousandth smaller. You say, well, I don't want to be right up there at the limit. I'm going to dial it down a little bit, take an extra thousandth off, and so my shaft now measures, my second shaft measures 1 inch 4 thousandths. So it is a thousandths smaller in diameter. What size tolerance zone do you get for straightness? Well, this is the easy part here. For every thousandth that you give up, every thousandth that this shaft gets smaller, you add that thousandth that came off the OD, and you add it to the OD of the tolerance zone. So at 1 inch 4 thousandths, the tolerance zone is a diameter of 11 thousandths. And you just keep going all the way down to the bottom here. So if you make that shaft, if you start making your shafts at 995, right at the low limit, now that's kind of precarious, but if you can do it reliably, you get 20 thousandths of diametral tolerance zone for the straightness. Okay, so it's basically, and this doesn't matter whether it's a male or a female feature, the tolerance zones work exactly the same way. As the feature goes away from maximum material condition, in this case a male feature, a shaft, as the shaft gets smaller, the tolerance zone gets bigger. They work in opposite. Similarly with a bored hole. At maximum material condition, when the bore is at its smallest, it has to be at its straightest. As you open up that bore, as you get more clearance in there, it can be more bent or less straight, and by the same ratio. So even though the logic is switch as to which limit is maximum material and which one is least material condition, the tolerance zone adjustment is exactly the same logic. So how do you play this game? Well, you pick up a part, you measure it, you say, well, this one hit right at split limit. This is exactly where I want to be. I have taken 5 thousandths off from maximum material condition. I know then that my straightness tolerance zone is 15 thousandths in diameter. So I got a 50% bonus by getting away from the limit and increasing that shaft size, or reducing that shaft size. Again, as you head down towards least material condition, the tolerance zone continues to get bigger, but you're getting close to your limit. So you risk sort of scrapping parts in order to get that tolerance zone. Now, under what scenario would this ever be useful? Well, let's say you're making shafts for rollers, and those rollers are going to be heat treated. So you turn them right to 1 inch 5 thousandths, you heat treat them, they bend a little bit. They can only be bent within a 10 thousandths tolerance zone when they're that large. As they get smaller and smaller, they can get more and more bent. If you think about it, if a pin that you've turned is at its maximum material condition and it has to go into a bore with a close fit, if the pin is bent, it's just not going to go. What would you do in that case? Well, you do one of two things. You would bore the hole out more, or you would turn the shaft down a little bit. In both cases, no matter which one of those you do, you're going away from the maximum material condition. That allows that bent shaft to go in. It just opens up the hole a little bit, and the bent nature of the pin doesn't matter at that point. So this is the bonus tolerance that you're going to hear talking about, but in order to evaluate it, you have to measure that actual part. If you've got a basket of 100 of these, you have to measure 100 diameters, and each diameter is going to have its own size tolerance zone. This is again a critical aspect to making sure that if you're making two parts in two different locations, when they come together, they will fit. And that adjustment of the tolerance zone is something that you probably have done yourself and never even realized it. When you're trying to fit a piece of sheet metal over a frame and the holes aren't lining up, you open up one of the holes, you have done this. You have adjusted the tolerance zone, the positional tolerance zone in this case, by reducing the material condition. Going to a least material condition in a hole is opening it up. Alright, so in most cases, I would say 90% of the cases where you're going to see a material condition modifier, you're going to see it as an M, as a maximum material condition. The least material condition modifier works in a similar but reversed logic way. So let's look at that one. If for some reason, I can't think of a reason why you would do this, but you could say that the modifier is at least material condition. If that is the case, then if you say it out loud, it'll become obvious to you that I have a straightness tolerance zone of 10 thousandths when the feature is at least material condition. So when this shaft is at the smallest, I get the smallest tolerance zone. And so on and so forth, 1,000th at a step. So if you want to have the most tolerance zone for straightness, in this case, with the least material condition modifier, you would have to make the shafts at their maximum material condition. Now again, this probably wouldn't happen. There are instances where you do use this. It's It's used to prevent thin wall conditions when you're drilling a hole into a thin component. And it works very well in that regard, but you won't see a least material condition modifier used very much at all. But if you do, you understand the logic is that this tolerance zone applies only when the feature is at whatever condition is noted there. In this case, least, you get 10 thousandths. If it's a max, you get 10 thousandths when the feature is at maximum material condition. So it's a dynamic adjustment of the tolerance zone based on how much material is in that feature. And again, you can kind of see that you got to keep your numbers straight. You got to keep your maximum material condition limit straight, least material condition straight, and you have to sort of chart what size tolerance zone you're going to end up with based on whatever diameter that feature is at. But it is always a thousandth for thousandth. Whenever you deviate from whatever limit is there, as you get smaller in this case, you go down a thousandth, you add a thousandth to the tolerance zone diameter. It's as simple as that. There's lots of software that does that. I think CMMs do this automatically now. But you can do it, and now you understand why you do it. And it allows you, as a manufacturer, if you're making these parts, you can pick what tolerance zone you want as long as you can control what the diameter of the feature is. If you can keep it right in the sweet middle, you'll get an additional 50% of the tolerance zone. And again, that sometimes is the difference between an expensive part and a very difficult to make part. Okay, so this is, again, a brief summary. I'll try to highlight some of this as we go along. We're going to see material condition modifiers applied to the feature. When we get into orientation now, we're also going to have an additional box here. I won't draw it here because we know that we don't put a datum here, but in the datum box of an orientation control, that's a feature too. That datum is a feature, and we can adjust the tolerance zone based on the size of the feature itself or the datum feature. So you can actually stack up these modifiers and you can end up with a pretty large tolerance zone if you're not careful. And then again, that carefulness is something that has to be trained into engineers. You don't just say, oh, I'm going to go ahead and do it because I can, because it does adjust the tolerance zone, and you can end up with some pretty bad parts being accepted based on not thinking through what all that additional tolerance is doing to your parts. Okay, so let's leave it at that. I want you to review this. Make sure as we go along that you're thinking in terms of what is the adjustment to the tolerance zone based on the limits that are established by the dimensions. Okay.